on dense vibrated granular media across jamming from stuck liquids to soft solids.
Okay, so yeah, the title changed a bit since I've added some new piece of work. But the thing I'm going to be talking about today is work in collaboration with Bob Berenger, Olivier Dojo, and Antoine Seguin here. So I first think, jamming is relevant to describe granular flows, but I think it's just one idealized model, and maybe it's not directly relevant, but I hope it can someday somewhat be helpful. So first, let me recall you briefly what jamming is. It's an idealized picture that stands at 0 temperature, and that the basic picture is here. You have soft particles that are in a box. You increase the size of the particles or decrease the size of the box, and they start to touch, and then they just overlap. And from the point they start to touch, the contact number, average contact numbers start to increase and scale with the distance to this point. And this point is not absolute, it just depends on the protocol. And interestingly, the bulk and the shear moduli also scale with the distance to the isostatic point, which here is recasted in a number of contacts. So, but this is an idealized picture, and when you ask your friends who do numerics, you ask them what strain do I have to get if I want to measure this, they say, oh, it's 10 to the minus 10, which is something you never get in the experiment, right? So what we, as an experimentalist, what we would like to ask is, what is the effect of finite strain? And what is the effect of agitation, as in a flow, or even more for small grains, you can have thermal or mechanical agitation. So I'm going to tell you two stories today. The first is we address, by locally probing packing across jamming, we address the effect of finite strain, and then we'll study the fluctuations. So to study the strain, we take a bunch of photoelastic disks that lay in a board, and they are confined in a cell whose surface can be tuned thanks to a piston. And then you combine like photoelastic techniques to measure the position and the force, stress tensor, contact network, everything. Then you just measure the contact number, and what you get is this as a function of packing fraction. You get this constant, and then it starts to increase. So, we identify this kink as a signature of the jamming transition in our system, where here it increases, and here it's constant, it's slow, and it's residual effect due to friction or because the system is not perfect. And actually, I doubt there's any real realistic system where you can have really unjammed structure. So this is our system. Then what we do is that we add an intruder and we inflate it. So let me show you a movie of it. Hopefully, yeah. Does it come? Yeah. So this is red. It's really like inflating by 10%. So here you have the reconstruction of the pressure. You see the force strain of pressure in this grain, and here you see the displacement as this guy is inflating, and the movie is inflating it. Let me play it again for you. So you see that, yeah, there's a radial symmetry here, and it's kind of increasing also here. So what we do in the following is we use these quantities, and we associate per grain displacement, strain, and stress tensors. So so what I'll do through all the talk is like I will average all over the angles there. And so first the displacement here, we see that with respect to the distance to the intruder, it's like kind of is consistent with the -1 Power law, which is what's described by just volume conservation. If you look at the log of the strain tensor, it's scaling as minus 1.5, which is different what from elasticity tells you. Elasticity would tell you -2. And even more wild, the log of the stress tensor just scale as r to the -1, which is some kind of, yeah, it's much broader than what is expected from elasticity. So now we have the stress, the strain, we have the stress. Let's try to get the shear modulus, because the shear modulus is the derivative of the stress versus strain. And for low strain, this is what we get. We get constant G, and then we get an increase, a sharp increase, and then it's like roughly constant. If we do that for a lower strain, oh yeah, and so we, so we see like this sharp increase. It's kind of consistent with what has been done by numeration people when they study frictional jamming, where they see not the scale, the G does not scale to 0, but it just drops. If we go to larger strain, we see that the same tendency, but it's lowering. And we see that there's what we call the strain weakening effect, that as we increase the strain, the shear modulus decrease. This is valid when we are high packing fraction. At low packing fraction, it's more constant. You see the same information here, and you see that this G scales with the strain to the -alpha, and alpha also feels strongly the jamming crossover here, as here it is roughly around 0, and here it's 0.5. So this is the first message of this talk. When we probe experimentally around the jamming point, we don't see any linear response. On the contrary, what is done in simulations, we see a strain weakening effect. So we don't understand fully why this strain weakening effect is due to contact that break. So or is it due to another clue we have is like dilatancy, and we see here a map of the trace of the strain tensor, which is just tell you how much your volume increases locally, and you see that here the volume increases, and here far it slightly decreases. So you have two different regions, and when you compute how much the bulk modulus, so the trace of the stress over the trace of the strain tensor, you get two different regimes. When you close to the intruder, you have a negative bulk modulus, which means like your pressure increase, but your media just dilate. And far from it, your pressure increase, but your media compress. So, and this is, yeah, and I think this is due to, but we are not, it's just preliminary for now, it's ongoing work, that is due to Reynolds dilatancy, because here you strongly shear the system, and that's where you end up with, negative, increasing pressure while you decrease the volume. So, let me now turn, so that's the first take-home message of this talk. You have a gap of the shear modulus value strain, so we can probe a little bit of the physics of that's prescribed in numerics, but the driving blurs it super quickly. Let's now turn to vibration. So it's the same system, but I plug in vibration, and so the first thing we see is like the structure is frozen, so it's a glass. No granular range here, and I see nearly the same thing for the number of contacts. There's the king that signs a structural crossover. If now I turn to the dynamics of the contact network, I just use a quantity that tells me if the contact network has relaxed between two time steps, and it's equals to 1 if it's not, and 0 if it's relaxed. When I average it, I see two different things. For large packing fraction, it's constant, no relaxation, and for low packing fraction, it starts to decrease. When you look at the characteristic times, you see that this one just seems to diverge at the point at which also the number of contacts start to increase. So the structural crossover is also associated to a dynamic crossover as the relaxation time of the contact network increase. So what's this relaxation due to? You can, instead of looking at the average, you can look at the variance that tell you how much grains relax at the same time. It's called dynamic heterogeneity. If you do that, you see that versus time you have a maximum. So there's a time at which dynamic heterogeneity is maximum. You report it versus packing fraction, and you get a maximum. But the maximum is at a different point than the one at which we had the static crossover, the structural crossover. So we have two crossover. So it's a bit weird. And so this is just a quick slide to show you that when you look at the dynamic heterogeneities of the displacement, you get the same when you look at the dynamic heterogeneity of the contact, although it seems to give you different information in the packing. But still, the key message here is that at one value of vibration here, we have two crossovers. And if I recast it with this picture, what we want to address here, what's going on when we decrease, can we get closer to the jamming point? So what we do is that we do all the same machinery, and what we see is that this is the two crossovers, and I decrease the vibration, and we see that they get closer here, and we see that the peak, so the fluctuations get bigger here. So this is the picture we end up with. We have two merging crossover and increasing fluctuations, and actually this is reminiscent of what you have in the vicinity, in the supercritical phase of just the critical phase transition. And these lines, where you have maximum of susceptibility, thermodynamic susceptibility, merge, and the susceptibility also tend to diverge at the same point. These are called Widom lines. So the question is, do we probe the Widom lines for the jamming transition? To do that, we have to do some benchmark and to compare with what we've done for like real thermal frictionless soft spheres. And this is a nice piece of work that has been done by Berthier, a collaborator, where they measure also very similar things. They have a number of contacts that just increase, and the increase is smoothened as temperature increases. And also they have dynamic heterogeneities that are maximum a little bit away from jamming, and the magnitude decrease as temperature is increased. And they have identified the scaling region here and placed different colloidal experiments for now, which are far from it. Question, where are we with our grains, shaken grains? So we do some benchmarks. So we compute the mean square displacement. We see a ballistic regime, then the plateau, and then some leveling off here. If we measure the amplitude of the plateau, this is what we get versus packing fraction here. And we have this is all different experiments we have. We compare it to what's done in the numerics here. So it's kind of similar, ballistic plateau. And this is the MSD, the mean square displacement plateau versus packing fraction for different temperature. So what we do now is just we look at how much a particle vibrate, because this is what the information we get here. And we just measure the temperature from that. And what we get here, if you look at the number, we are close to 10 to the minus 7, 10 to the minus 8. That means that we're there. So from the analysis of the dynamics, we can claim that our experiment, although they're different because it's frictional, it's not temperature, probe the same physics as than the one which is probed in thermal soft spheres frictionless. And this is the second message of today, together with the first. We see strong signature of the jamming transition close to it, but as soon as you increase the drive-in, should it be strain or shear, you just smoothen it. And with that, I'm happy to thank you and take questions.
Thanks again for doing the presentation quickly. So we have plenty of time for questions once again.
Yes.
Yes.
I'm a little puzzled by your invoking one single J point in all cases that would be at some place on the phi axis. Because if we have ordinary grains with friction, you know, we can form solid states, that is to say jam states at different solid fraction by different procedures. So the solid fraction at which the system will form a solid, will jam, it completely depends on the procedure with which we assemble the grains, that's one thing. And also in all those considerations, I wonder if, you know, that there is sometimes, maybe it's not your case, but in this kind of studies, occasionally I'm under the impression people tend to confuse the jamming point defined as the point where a solid forms if you reduce density, if you compress the system on the one hand, and on the other hand, the jamming points corresponding to the density of the quasi-static continuously sheared system, which is in other words, the critical state density, above which you cannot shear the system continuously. So, what is your reaction to that? How
Okay,
do you,
so
when you say the jamming point, what does it mean?
So the jamming point is experiment dependent. So as you say, you have one jamming point per experiment, and that's why all the experiments I've done here, I've done them so that I don't have the same jamming packing fraction for each experiment. That's why here I have an epsilon and not a phi, because this epsilon is a reduced packing fraction. It's phi minus phi dagger, which is my structural crossover for jamming, and it varies from experiment to every experiment. So I agree with you, but the strong feature of jamming is like things scaled with distance to it. So I don't claim there's one point, I just claim when I visit this point, so I have to carefully prepare my system, compress it, study the pressure, study the contact number, I spot it with the contact number, and from it I just study, the quantities varying from it. And that's what doing this experiment is painful, because you can only do it once, and you have to prepare the packing carefully and then studying it. What people do in numerics, they can have the same packing. So here they have only one phi j, because they always start from the same. They always quench from the same packing, and then they reproduce. That's why they can compare it to phi j here. But yeah, in real life you cannot do this. Does that answer your question?
We have another question.
Yeah.
It's a bit a related question, but it's true that how much your driving looks like a shear, and how much does it look like temperature? And it's true that if you reach critical state by shearing a lot, you also have singularities. It seems that in simple models, the sort of heterogeneities of the dynamics are the same in both cases.
Yes.
But some other aspects are different. So, do you think your driving is more like a temperature, or is more like really shearing
on the first or on the second case?
Like,
Second case?
yeah, how do you excite your system?
I shake it from below.
Back and forth like that?
Like this, from below. So the structure doesn't move. I don't know if you've seen the structure, no neighbors ever change on it, or nearly no neighbor ever change. So it's really we study one, here. This is just two Voronoi cells of like before and after for the loose packing fraction. So you see no thing. So it's really we study, and it's really just the contact network evolve, and we have small vibrations, like and I think dynamic heterogeneities are more like you have zones that vibrate at some point and more at the other, and then they exchange rules.
Do you create a gap in the system when you vibrate like that, or at the top or at the? Does it stay homogeneous during the vibration, or how does that?
Yeah. It's that you shake it above the accelerations required to sleep on the table, if you want, and then you just when you just take and the dynamics is there, so you have really. I'd have to, but what's going on is really summarized by that. Of course, there's a real oscillation when I do like a high-speed camera experiment. That's what I did for getting these decades there. But then if you remove this oscillatory motion, that's what you get. So you get really something that smells like something ballistic. So hopefully, what we claim is that our driving just transfer into the grains motion into like this kind of motion, like ballistic, and then here you feel your neighbors and you just don't.
We have time for extremely short questions. Just go to people asking them, I suppose. Yeah, very good question.
Okay, just to get a feeling for the experiment, what is tau? What is the time scale?
So this is millisecond, and this is 40 minutes, I guess. Yeah, and so I just rescaled it with the elasticity of one particle. So it's rescaled with m over k, where m is the mass of a particle and k is the stiffness of a particle.
Excellent. Thank you very much.